introduction to unmanaged code was what we originally decided to call it. However, I decided to change the term from unmanaged because that's really a Windows specific term. And as you'll see, we're not going to be specific to any particular operating system or anything else. So a gentle introduction to pointers in memory. Welcome. I will warn you all at the beginning. I have a suspicion that this is going to go a little bit longer than the hour that is scheduled for. I will not judge you if you have to drop. But on the other hand, if you're able to stay and you have questions, I will stick around as long as there are questions to answer and do the best I can with them. You can also ask questions during the talk. I can't guarantee that I will get to them, but if I see a question that is related to a particular slide, I'll either answer while I'm on that slide or I'll come back to it at the end and I'll go back to that slide so we can talk it through. So with that said, thanks again, and let's get started. You'll see, or you should all be able to see my little red dot here. I'm going to use that to highlight things. So if it's not showing up for you, please let me know. We'll go ahead and get started. So this talk is called A Gentle Introduction to Pointers in Memory. You've probably heard the term pointer used before, maybe as a nebulous concept, maybe as something a little bit scary, or something advanced. We will talk a little bit today about what pointers are. We're going to go into plenty of detail on that. But before we do, let's talk about, from a meta perspective, why should you learn about things like pointers in memory? Why would you probably know that these are very deep down at the base level of the system concepts. You know, they're kind of underpinning concepts. And so if you're writing in a higher level language, if you're writing in C# or Python or whatever, you may not encounter pointers all that often, if ever. But there's lots of really good reasons to learn about them regardless. The first is that, to be frank, there are lots and lots of jobs, what I've kind of bluntly put as money, but obviously doing an interesting job is more than just that. There's lots of jobs that rely on this kind of knowledge. Game design, we were having a conversation about Unity and Unreal before we started here, is a big one. Where a lot of low-level code is still used because of how efficient and fast it is. Embedded systems design, when you're manufacturing something like the speakerphone that I'm using to give this talk right now, or the USB fingerprint scanner that I've got right over here, or really any piece of consumer technology that requires software engineering but is not a full-fledged computer or smartphone or similar, an embedded system as we would call it, absolutely will use this stuff. It is still the standard. Operating system engineering, C and C++ in particular, are the languages that underpin the entire Linux kernels written in C. Pretty much all of OS X's kernel, the Darwin kernel that's way down there, is C and C++. I think some of it now may be Objective-C. And even Windows is also mostly C and C++, and even assembler the further down you get. The last piece is security. All of these incredibly fundamental things using this technology means that there are security implications to using it correctly. And as you'll see, there are a lot of security concerns that come about when we do not use these technologies correctly. So all of those things that you can do with them in terms of concrete job options are a great reason to learn. The second and third reasons to learn are related. And the second reason is really just, they're cool. These are some of the absolute most fundamental pieces of technology that power everything that your computer does. And as you're going to see, all of the things that we're used to in our higher level languages when we develop and write code come from these concepts that we're going to talk about today. They're awesome. They're some of the most interesting stuff that you can learn about, in my view, on that line between theoretical computer science and practical applications of computer science. And my hope is that you all find this as interesting as I find it, because it's really going to be a look at the sort of the magic that really makes things work and those key abstractions that have allowed us to develop technologies of all kinds to the point where they are today. The last point is wisdom. If you understand what your system is doing at these low fundamental levels, even if you're not doing it all the time, if you understand the security implications of choices that you make, even if you're not the one writing pointers or allocating memory manually, you're going to be a better developer in whatever language you work in, because you'll understand why things that might have seemed magical before, things like referential integrity, garbage collection, recursion, and self-referential code, why those things work the way that they work. It's going to help you understand a lot of that stuff. For example, if you have a program that is going crazy and running out of memory, this talk is going to help you understand what may be happening under the hood that can cause things like that to happen. And even though the solution may also be in a higher level language, my hope is that by having heard all of this thing, it's going to feel less daunting trying to solve some of these nebulous problems or problems that occur at a system level. So who am I? I'm Max Zimon. I'm a software engineer currently at Olo. I got my Bachelor of Arts in Computer Science and Cognitive Science from Case Western Reserve University in 2016. That was my first exposure to these topics, and I will tell you right now that I did not understand them at all until I went to work at Musicnotes, which is a company that sells digital sheet music, or like Kindle for sheet music. And at Musicnotes, I was working on sheet music editing and publication software that dated back to the 1980s and had code in it that was written in ANSI C, which is one of the oldest versions of the C programming language that's still in use today. And I had to learn these concepts again, and it took a little while to get them, which is okay, because these are, again, fundamental but complex topics. Now I'm at Olo. I don't write a lot of C or C++ or direct memory management code anymore. Olo is a company that makes the middleware for restaurants. I'm happy to talk a little bit more about it at the end if people are interested. But essentially, all of the online ordering and ordering apps that you might use for any large restaurant, we do. All of the delivery negotiation and menu synchronization and so forth to keep restaurants synced with all the different platforms that would sell their food, DoorDash and Postmates and Uber Eats and whoever else, we do all of that. And we work for the restaurants. The restaurants are our customers. So those are the people that I work for now. And then this is my cat Scout. She's right back here. Hi, Scout. She's sleeping, but you'll all see her quite a bit in this talk. And as we'll get to, she's very important. So here she is. You can always refer to her if you become confused. And as you'll see in a minute, she's going to be helping us a lot. A couple of disclaimers, though, before I move on. As I said, I'm somebody who learned all of this stuff in college, forgot it all, maybe never fully understood it, relearned it for my job. And so I am not an expert or an academic. I am an engineer who has to use this stuff or has had to use it on a daily basis. And so the understanding that I've developed that I'm going to give to you today is very much on a daily basis, when you're using this, how is this going to work kind of understanding. It's not a perfect academic description of the concept. It's not purely theoretical. We're going to be pretty close again to that line between theoretical and practical. And I'm not going to be able to cover everything. So we'll talk a little bit about what we really can cover in this talk, and how we're going to handle things that we can't. My goal for you with this talk is to come away with a better understanding of some of these concepts I have listed. These are complicated things. It is not uncommon to not fully understand all of it on the first go, and that's okay. But what I would suggest is I'm hoping that you will get quite a lot. And I think that if you are an engineer who's got some basic fundamentals in a couple different languages, you've done some basic projects, this stuff is not beyond your grasp. This stuff is going to come to you, and it's going to start to make sense. And even if it takes, whether it takes shorter or longer for you to fully get it, I want to start you on that journey today. I think it's going to be worth it. And so I'm just hoping that when we come out of this talk, you're going to have an understanding of what memory is from a program's perspective, what data types are, as we refer to them in a statically typed language like C or C++, what a pointer is, again in C or C++, but also in general, also the theoretical concept of a pointer. We will have a good definition of it, and how pointers are used in languages like C and C++ and Rust, but also in a theoretical sense, so that you can understand fundamentally the most important thing here is, why does it matter? Why would we use these structures? Why are these important concepts to understand? My hope is that when you come out of this talk, if there was one thing I could give you, it would be, this is roughly what a pointer is, and this is why I should know what it is. That's the most important thing. Everything else is icing on the cake, as far as I'm concerned. So how are we going to do this? I'm going to give you as many visual examples as I can. We're going to have tables. We're going to have images. We're going to try and make this as much something where you can look at a little bit of code, look at some charts and tables, and really get a sense of what's going on, rather than me just telling you this is how it works. We are going to give our examples in a language that is basically C. There are some conventions I'm going to use or not use, but fundamentally the examples in this talk are written in more or less standard modern-ish C, with some exceptions. And we're going to talk a little bit about some of the other languages. I've mentioned C++ and Rust. We'll talk about those at the end. But for the most part, the convention here is going to be C, because C is really the language where this concept most became popular. It is really the language where these ideas came into their own. The last thing we're going to do is we're going to have a rule that I call the Scout rule. I mentioned before that this is my cat Scout. She's always right here to help you. She has her bow tie on, which means it's time to be serious and do work. And whenever there are things that we can't get into because we don't have time, but there are a lot of good explanations for, there will be a picture of Scout, and you will know that what that means is there's lots of great reasons why things are the way that they are. And if you have questions about it afterward, maybe we can talk about it a little bit, but just to get into it in the basic talk, for now, the answer is Scout does it. It's Scout's job. She knows how to do it. And Scout's telling you that it's going to be this way. And so for the purposes of the talk, that's how it is. Not because we couldn't go deeper, but because to go deeper would take more time than I have. Let's get started. What is memory? Memory is another one of those terms where people have different understandings of what they mean by it. You might think memory and think, oh, it's the RAM, the physical sticks of RAM in my computer. You might think of RAM and think of your memory and think of your hard drive, because that's where data is stored permanently. From a program's perspective, none of that is what memory is. From a program's perspective, when it is running, memory is a big chunk of data that the program gets to manipulate however it wants. The program is also loaded into memory, but the program doesn't know that. The program doesn't know or care where it's loaded. All it knows is it's going to move data around and do things to data in a space that it happens to have. So the first thing we need to talk about is, how does the program understand the structure of that space, and how does it manipulate the data in that space? To understand this, we've got to go all the way back down to the very fundamentals of how computers represent numbers and data. Every piece of data in a computer has a numerical representation of some kind, and those numerical representations are strings of zeros and ones that we interpret to mean different kinds of thing. So if you were just to look at raw system RAM or the raw L1 cache of your CPU right now, it's just a whole bunch of zeros and ones. It's a bunch of on or off signals. We'll say for this talk that 0 is off and 1 is on. That's not always what it is, but just for this talk. And it's not really comprehensible just staring at it that way, not just to you, but also to your program. So to make it easier, we have some names and terms and we break things up. We call a single 0 or 1 a bit, where a bit can be true or false, 0 or 1. And we call a set of 8 zeros or ones a byte. So each of these, separated by a space here, is 1 byte. So a byte is 8 bits, and then megabyte, kilobyte, etc. A kilobyte is 1,000 bytes, a megabyte is 1,000 kilobytes, and so on. That's why they're different from megabits, which is a single 0 or 1. 1,000 bits is different from 1,000 times 8 bytes, which is, again, a byte is 8 bits. So we break them up into bytes because that's a convenient little chunk. And then we have to decide what they mean. Now you might be thinking, again, how is this stuff represented in the hardware? How does the system decide what set of memory to give you? Scout does that. All of that is down to Scout. She decides where in the hardware it goes. She decides what addresses to give you. All of that is up to her. And we're not going to worry about it for now. All you need to know is, as a program, you're going to have a chunk of memory that belongs to you that you can manipulate. And inside of that memory, you've got bits, which are separated into groups of 8, which are bytes. Now, we need to have a way to refer to these groups, right? We have to have a way to know which byte we're talking about. So we have this concept of memory addresses. Those are simply numbers that refer to a specific set of bytes or a specific byte. So here we've got an address space that starts at 1 and goes to 100. So you've got 100 addresses there. Address 0 is a special concept that we'll talk about a little later. And you can see that there's specific data. This is the same data as what we saw here on the previous slide. From addresses 11 to 19, we've got this sequence of bytes. So if we say the byte at address 11, we're talking about this one. If we say the bytes 4 bytes from address 11, then we're talking about 11, 12, 13, 14, this collection of 4 bytes, and so on. And when we are using our memory, we also need to indicate whether the memory is in use. So Scout will keep track. If you tell her that the memory is in use by the program, that the program has decided to put some data in this address that it is allowed to put data in, we'll mark that data as in use. Scout will mark that data as in use for you. And so we know now that something, what? We'll come back to that. We'll talk about that soon. Something is using this data. So the byte at address 11 is in use, and the data in here is data that is being used by some part of the program to do something. What does that data mean? What is the purpose of address 11 and 0110010? Well, that entirely depends on our interpretation. We can consider any chunk of memory, any sequence of bytes, to be whatever we want. It's all about how the program considers it. You're probably familiar with the idea of types. If you ever worked in a statically typed language, like C, C++, C#, then you're familiar with the idea of or Java, there's integers and floats and decimals and chars. I pronounce this CHAR as car. Some people say care. I'm probably going to say car because that's what I'm used to. I don't guarantee that that's right. So these data types, whatever they are, in C, data types have a meaning. So a car represents a single letter, a single alphanumeric character, or in some cases symbols, but generally alphanumeric characters. And an int represents an integer number between about 2.1 billion and negative 2.1 billion. And we need to say, well, I need to represent those in my data in binary. How much space do I need to do that? How many bytes do I need? Well, in C, the answer is that for a car, you need 1 byte. So this piece of binary, if you consider it to be a car, has a value of B. This piece has a value of I, and so forth. For an int, to express all those numbers, because remember, we don't know whether you're expressing the number 10 or the number 1,651,074,848. Because you have to represent that whole range and you don't know what's going to be in there for sure, you have to have 4 bytes to do it. You need 4 bytes because the maximum and minimum numbers in there at most take up 4 bytes. So this value, this set of 4 binary bytes, if you put that into a converter from binary to decimal, you're going to get roughly this value. Shubham asks, how many addresses are there on average in 8 gigabytes of RAM? Well, if you're addressing one byte per address, then you can do that math. A gigabyte is 1,000 megabytes, and a megabyte is 1,000 kilobytes, and so on. You can do that math, and there's a lot of addresses. This gets into the idea of addressing spaces and how many bytes per address, which is its own complicated space. For the purposes of our memory, we're just going to say that there's 100 addresses available, and that each address corresponds to 1 byte. I would be happy at the end to get into some more details on how that actually works in live systems, but it is complicated and not part of this particular area. So in any case, if we choose to interpret 11 to 14 as an integer, then we're using those 4 bytes to have this meaning, this value. Likewise for 15 to 18 here. And you could do, 19 to 23 and so on. This is how we're choosing to interpret it. And we're saying, so the memory, remember, is in use, and we're interpreting it as one of these kinds of things. We get to decide what it is. We get to decide what it means. It has no meaning on its own until we start deciding. So with that in mind, when we want to declare a variable and we want to consider the meaning, we want to set a meaning for some piece of information, how are we doing that? Here is a very simple C function. This probably looks like a million functions or methods you've seen in a bunch of different languages, except maybe a little bit more explicit because C is statically typed. You've got an integer as your return type. The function's called getCatCount. The underscore casing is typical C language conventions, which is mostly what I'm going to follow here. You've got an integer called catCount, which you're setting equal to 42. Now, you could be calling another function to get this. You could be reading some other variable to get it. There, you could be doing some math. I've just set it to 42 to be easy. but it could be anything. The process we're going to describe is the same. All you know is we're setting cat count to some value that comes out to 42, which is on the other side of this equal sign. This is what we want cat count to be. And then we're going to return that value times 2. What does that mean from the compiler and the program execution standpoint? What does that mean from the standpoint of the computer and from C when it's trying to do this? What we mean is we're going to have a function and we're going to be inside the scope of this function. Things we do are only going to apply to this function. And we need to find a place in memory to store this value we've computed called 42. And when we find that memory, we need to call it cat count. We need to say that cat count is the name we're giving to this set of addresses, these 4 bytes. Here's the binary for 42 down here. These 4 bytes, which we're going to put into that space. So how do we do this? We look at our memory. And specifically, we look at a part of memory called the stack, which is where memory that is in the scope of a specific function in C lives. We'll talk more about the stack in a second, but we're looking at a piece of our memory, a set of addresses that we're calling the stack, and we're looking for some free space. We're looking for something that Scout hasn't told us is in use. So we say, let's find some free space. We look around and Scout says that addresses 16 to 19 are allowed. There's nothing in there right now, or whatever's in there, we don't care because it's not marked as in use by anything. So what we're going to do is we're going to say, okay, let's put my binary representation of the number 42 into those 4 addresses, and let's mark them as in use by a variable called cat count. So now we know that when we see cat count, what we mean is addresses 16 to 19, because you need 4 bytes, 4 addresses to store a single integer. And then Scout will say, okay, I will mark this memory as in use by that variable. And now anytime you use that variable, I know where to find that memory. Are there cases where data is scattered across memory addresses that are not placed together, I'm asked? Absolutely. We're going to get into that in just a little bit. But for the moment, we're going to assume that these addresses are sequential. And they need to be sequential because in order to define something as one integer, it needs to be a set of 4 contiguous bytes. So what does this code really mean? What this code really means is when I declare my variable here, I'm putting it in addresses 16 to 19. And when I read my variable to perform some mathematics on it, I'm saying 2 times, or the value times 2, the value in addresses 16 to 19. That's what this statement means. It doesn't mean return some mythical thing called cat count. It's being compiled and then interpreted at runtime to mean find the variable in this address. The address specifically is chosen at runtime, but we know when we compile that there's an address that will have this variable name associated with it, and that's where we'll look. Find that address, take whatever integer is there, multiply that by 2, and send it back. So again, these variables live in what's called the stack. This is a space for just the variables. You can assume that there's a space for just the variables in this function. Nothing else in another function can get to it because it's in what we call a frame on that particular part of the stack for only this function and not for anything else. So what's a pointer? We know that we can create a variable and set it to have a specific set of addresses in memory where its data lives. So what is a pointer variable then? Well, a pointer is a variable which stores as its value the memory address of another variable. This is a very formalized definition. So let's take a minute to break this apart and really understand what that means. We know that we can have a variable of some kind of type, right? The variable type for this is an integer. So what if we say, instead of an integer, I'm going to store one of these address numbers? What if I want a variable that says 16, but then when I interpret the meaning of 16, what I mean is the memory address 16? Because cat count, as you saw, stores the value 42. But what if cat count stored the value 16, and we said that it was a reference to a memory address called that had the number 16? What if we changed the meaning of that number so that it refers to an address in memory instead of just being a straight number? A pointer is a variable which stores as its value one of those addresses in memory. So what's the data type of a pointer? What does that mean? As I say, if you have an integer and that takes up 4 bytes, that just means that there's a set of addresses that holds that 4 bytes. Okay. If you have a pointer, however much space the pointer takes up, we can say that your data type for the pointer is both the fact that it's a pointer, so we know how much space storing one address takes up. And then we also say, well, what's the kind of thing that we're going to talk about when we look at that address? When we look at the address that that pointer is representing, what kind of data are we intending to find there? So a pointer's data type is both, yes, I'm storing an address in memory. The number that I have, my binary that I've got allocated to me, that binary represents another address in memory other than my own. And that address in memory other than my own is interpreted as a particular kind of thing, is interpreted as an int or a char or whatever. So pointers always have to have 2 pieces of information with their data type. You have to have the fact that it's a pointer, and you have to have the type of thing that we're pointing to. Let's take a look at an example of what this does and how this works in practice. Let's take a look at some new operators and some new language conventions that allow us to indicate that things are pointers. Here, I've rewritten the function that I just showed you, the get cat count function, so that the value we do the return on, that we calculate in return, when we return, is a variable that is based on a pointer. We have a pointer assignment statement here, int star cat count pointer equals ampersand cat count. We're going to go deep on what every piece of this means. So the first thing is an integer. That's our regular data type. That just means that whatever we're storing, it's got a size of 4 bytes and we're interpreting it as an integer number. And then we've got a star. The star is called the dereference operator. We're going to come to a formal definition of that, but for the moment, let's consider that that means this thing is a pointer. This thing is a reference to a memory address where I could find an integer. It is not that integer itself. We have our variable name, that's the same. We have our variable assignment, that's also the same. We have a reference operator. That means cat count here is going to store a memory address. There's a memory address that cat count is associated with, as we saw in our table before. We want to know that address. We don't want to know the value right there. We just want to know the address. So if we stored it at address 16, as I showed you earlier, then this value, ampersand cat count, is going to give you a pointer to address 16. Now, what's this doing? We'll come back to that. What's the difference between int star with a space and then int space with a star? There's not a difference. That's semantic. Scout knows all the reasons for that, and we can talk about them with her later if you'd like. So let's talk about these new operators in some more detail. Let's talk about the star and the ampersand. These are better referred to as the dereference and reference operator. There are some other terms for these operators that different people will use. I like these terms because the important thing to remember is that a pointer is referential. A pointer tells you the location where something else lives. So we call them a dereference and a reference because that's what they do. The dereference operator, when you're declaring a variable, means the variable that I'm declaring right now is going to store a pointer. It's going to store a memory address. And at that memory address is a thing of the type that I provided. And when you're using a variable, it means look at the address stored in my pointer, go there, take the data and use that data for whatever I'm about to do and interpret it as the type that I provided. We'll come back to exactly how that works in our example in a moment. But the reference operator means when you put it in front of a variable, figure out the address that this variable has been given. Figure out where in my memory banks I put the data that this variable resolves to or relates to, and give that back to me, and I'm going to store that separately. If it's used in front of an integer, then the address you get back is an integer star, an integer with the dereference operator attached to it, which is to say an integer pointer. Whenever you use this reference operator, you're going to get a pointer back. Whenever you use the dereference operator, you're either declaring a variable that stores a pointer, or you're going into a pointer and finding the value that is at the location it points to. So let's actually go and talk a little bit more about what a data type for a pointer is. As I said before, when you put the star in front, you're getting a pointer. So the data type is pointer, because it's one kind of thing. These two things are both pointers. They're both addresses, which take up the same amount of space to represent, but they're pointers to different kinds of things. So again, these are different data types that have the same size and are both pointers. An integer is a pointer to a memory address that has 4 bytes of data starting from that address. A car is a pointer to a memory address with 1 byte of data. Here you can see a bunch of the common data types in C and how much data they can represent, the numbers they can represent, and then their size in bytes. So if you put a star in front of any of these, if you put the dereference operator in front of any of these, what you're saying is a pointer to a memory address that stores this many contiguous bytes worth of information. That's all you're saying. It's those two pieces. With that in mind, we can look a little bit more at our example. So first of all, we now see that we're using the reference operator here to refer to cat count pointer. So we're saying this is a pointer to an integer. There's an integer, 4 bytes of data, and we're storing the location where that data can be found. And what location is that? Well, it's the location of this other integer. When we put 42 in, where did that go? Find out where it went, put that value, the value where it went, into cat count pointer. And now, when we want to read that, we're going to use the dereference operator again. So we're going to return. That's the first part of this statement. Returning is a concept that I'm sure everybody has seen in various languages. We're not going to get into what returns actually do in terms of how they manipulate the stack or how they change where memory is stored, but just know that it's at a high level similar to returning in C# or any other language. You're going to send this data back out to whatever called it. You're going to return the value that you find at this memory location. The star, remember, means go to that memory location and tell me what you got there and read that much data. So we're going to go into this memory location, which at this point is the location of this variable. And we're going to find that data. We're going to read it back out and multiply it by 2, and that's the value we're going to return. So we'll say, okay, find it in memory, and then return that value times 2. Now I'm asked, what is the size of the pointer itself? Shubham, and I really hope I'm getting your name right, says, what is the size of the pointer itself? That varies from system to system. That is an implementation dependent piece of information, and it depends on whether your system is 32-bit or 64-bit and some other things as well that I'm not going to get into here. But what you can assume is that it is always the same for every data type that is a pointer, whether it's an int star, a char star, or et cetera, because it's always storing one memory address. So it's a standard size for everything that you're running on the same computer, but that size will not always be the same as other computers. And Scout decides that size on the basis of information about how much memory you have and the architecture of your system and so forth. Now, what if we said this? What if we didn't use the dereference operator here? Well, there's data right in here without going to the memory address this refers to, but what is that data? That data is a pointer. That's a pointer data type. Now, this expression, cat count pointer times 2, that's valid, that's allowed, but that doesn't mean what we think it means. That's not an integer, that's an integer star, that's a pointer, and we said we were going to return an integer. So this function won't compile, because in order for it to compile, the thing you're returning has to match the thing you said you were going to return. We would need to put a star up here by this integer to return that pointer. And returning the pointer is returning something fundamentally different than returning the integer, because we're not returning the int, we're returning the place where the int lives. What can I do with this? What's the value of this? You can see where something lives in memory. So what? The compiler already knows where everything goes in memory. Scout's already putting everything in memory for you. She's taking care of it. Why do we need to know? Well, what if I told you that you can do pretty much anything once you know this? Once you know this information, you can create any of the fundamental data structures that underlie all of the computing that we do every day. I'm going to show you some examples. What's an array? You're probably familiar with an array syntax that looks something like this. This is in C#, but you've probably seen something like this, maybe more dynamic in JavaScript. You could see it in pretty much any language that you're going to use. You've got arrays that are just sets. A set is technically another concept, so I guess we could say a collection that is ordered of information, of data. Maybe if you've used Lisp or something like that, it could look a little stranger than this, but basically it's the same idea. It's a bunch of contiguous values of the same data type. So if I have an array of 4 values, then I have 4 slots starting from 0 where I can put integer values. I've chosen 5 and 6 arbitrarily here. Those numbers have no particular value except that they're integers. But here you can see that I've created my array of 4, and I'm setting the value at element 0 to 5 and the value at element 1 to 6. You've probably seen this kind of code a million times, and in C, it looks very similar. There's no new operator in C. There is in C++, but that's a different thing. In C, there's no new operator. We just say int array of 4 and give it a size of 4. But you can assign stuff to it exactly the same way. And fundamentally, you're doing basically the same thing. So what's the difference? Well, what if I told you that in C, arrays are just pointers with some special syntactical sugar on top? That is to say that this code, and I know it might look a little strange, so we're going to go into it in detail, but this code is the same. Accessing the value in the array at element 0 is the same as dereferencing a pointer to the first element of the array. These two values, these two expressions are identical. All an array is a set of addresses, and at each address we're storing an integer, and we're promising for the purposes of this array, going back to the question before, for the array, we're promising that those addresses are contiguous. So 16 to 20 to 24 to 28. So we have an integer starting at 16, an integer starting at 20, an integer starting at 24, an integer starting at 28, and so on. And you could have you'll have 6 of those. So when we create our array, what we're saying is, give me 6 addresses in sequence, each of which will store an integer. Okay, Scout says. Starting from address 16 to 19, you'll have the integer for the value 5, because that's what you've set right here. And then in 20 to 23, you'll have this value. In the value at 1, we'll talk about what this means in a second, and so on and so forth. If you don't set them explicitly, by the way, they are not set. This is a quirk of C. You must always set things explicitly or they're just garbage. Until you say that you're using that memory, the memory is not used. But fundamentally, we're just pointing. We're just saying, okay, here's my first index, my first piece of memory. I'll put whatever I want right there. And now we need to figure out how to access the next piece of memory. How do we get from address 16 to address 20? Well, we do math. Array of 6 at the first index past the 0th element, the first element. So at the second element, first index, equals 9. What that's saying is, go 1 integer's length, 4 bytes, past the first address here, and put the value 9 at the address we compute from that. So what this really means is, array of 6 points to the address 16. Array of 6 plus 1 is 4 bytes. The plus 1 means 1 integer passed. An integer has a size of 4 bytes. So array of 6 plus 1, 16 plus 4 is 20. So at address 20, store the value 9. There's a typo right there, that should say 9. But store the value that we've declared. And then everything else is garbage until we decide otherwise. Likewise, if we say return here, we're going to say, okay, the array starts at 16. I'm going to go 1 integer's worth of bytes past that in my addresses to byte 20, address 20, and I'm going to return whatever I find there. That's all it is. Arrays are just pointers with a little bit of friendly syntax to make them look nice. All of this in C is totally equivalent. And under the hood in other languages, they may not be doing exactly this, but this is very close to what they're doing. Now, arrays are nice, but arrays are a fixed size. You can't make arrays bigger or smaller than what you declare them to be at first, right? And arrays live on the stack. They live only in the scope of the function. So this array only lives in the function you've declared. So what if I want, as was asked before, what if I want a lot of memory? What if I want memory that's not contiguous? What if I want, or at least chunks of memory that aren't contiguous relative to each other? What if I want to have memory that doesn't go away when I'm finished with my function? For that, Scout has generously provided to us a function called malloc. Malloc stands for memory allocation, and it's one of several functions in C. There are a whole bunch of different ones that do very similar things, but essentially what it does is you feed it a size that is a size measured in bytes, and it creates a chunk of memory, it allocates a chunk of memory, sets it aside for you, and says, here you go. Here's your contiguous memory of that much size. So let's talk about what that means in practice. It means memory allocate. So we're going to get some kind of memory back, and we're going to have to decide what that memory represents. Scout doesn't know what we want it to represent until we tell her. So how do we use that? Let's look at this code. We can declare an array by saying int star, that's a pointer storing a memory address of the size int, array of 4, equals a cast to int star, a cast to an integer pointer, malloc, size of int times 4. Let's break this down, just like we did some of those other statements. What's the int star? We already know, that's a pointer. Array of 4 is the name, equals is setting it. Here we're casting, so malloc comes out, its return type is void star. That just means, for our purposes, some kind of pointer. That is a pointer to something, but we don't know the data type yet, so we can't really use it. So we're going to tell it the data type, it's an integer. It's an int star, a pointer to ints. And we're going to allocate 4 of them. We're going to take the size of the int. That's what sizeof does. If you pass in a type, it tells you how many bytes you need to store that type. Multiply that times 4. So the size of the int is 4 because it's 4 bytes. We're multiplying that by 4 because we want 4 integers. And we're going to have 16 bytes allocated, starting from the address that malloc gives us back. And then we can do the same array access stuff that we did previously. Array of 4 at 0 is 5. Array of 4 at 1 is 6. That's going to do the exact same thing that it did before. It's going to say, okay, starting from the first value I got back, set that to 5. Then skip that byte, the first, the memory address that we got back, go 1 byte down, one int down from there, and set that to 6. Travel 4 bytes from wherever this address is that it gave me, set that to 6, and so on. You can access it just like an array. Is it an array? Not exactly. It's anything. It's whatever you've decided to consider it to be. Because we said int star, we can talk about it like it's an array. But really what it is just a big chunk of memory that we're interpreting however we want. And this memory that you allocate with malloc, well, we don't put that on the stack. We don't put that only in the scope of your function. We put that in a place called the heap. Why is it called the heap? Well, in short, because it's literally just a big blob of memory that's been allocated at different times by different things. And it's not organized any particular way. We just get the memory that's available from it. That's all we do. Now, in reality, of course, it's more complicated than that, but Scout knows all the details and we don't need to worry about them. The memory lives on the heap and you're going to get back an address that points to what we call the heap. Now, memory that is created this way lives forever until you tell it that you need to free it. That's why it's not really unlimited, because once you allocate it, it stays around forever and eventually you could, theoretically, run out. More on that soon. The other thing is that you've only got so much memory here. We've only allocated 4 integers worth of space. If I try to access an integer that is 10 integers worth of addresses away from where I allocated, there's no guarantees about what that memory is. We could pretend that it's an integer. You can pretend that anything is anything, because again, we're the ones deciding what a piece of memory means. But if you do this and that memory hasn't been allocated, Scout's going to say, hang on, you didn't allocate that. I don't know what's there. You never told me what to think of that as. I'm confused. I'll give you the data back, but I don't guarantee that it means anything. And in fact, it could mean nothing, or it could be something that some other malicious person has put there. That's called a buffer overflow. If you access memory that you did not specifically allocate, if you go past the 16 bytes that we've allocated here, and you went to byte, well, 4 times 10 would be 40, because 4 is the size of the integer, times 10, which is how many bytes from the beginning of the memory we want to go. You go 40 bytes away from this, there's no guarantees about what you're going to find there. Dragons, monsters, anything. So let's take another look at how exactly this works. Remember that this is an array. sort of, that lives on the heap, and that the memory has to be freed. Well, here's the allocated memory. This suppose now that these addresses 16 to 28 are on the heap, not on the stack. All we do is we say that they've been allocated. We don't say what variable because we don't know. It could, any variable could have them. Array of 4 happens to know this address 16, but anything could know the address 16. All we know is that we allocated it and we haven't freed it yet, and it's storing the data that we care about. Note that this data here, obviously there's going to be 4 bytes here, not 1. This is just showing you that last significant byte that has the value 5 in it. And again, if we don't set anything, just like on the stack, if you don't set it, then it doesn't have any meaning. There's nothing in it until you set it to something. So if you did size of car instead of size of int, I'm asked, then array of 4 at 0 would be 1 byte instead of 4. Well, array of 4 at 0 is just a value, it's just the address. But if you did array of 4 at 0 plus 1, you'd only go 1 byte over. So if array of 4 at 0 pointed to address 16, then doing array of 4 at 0 plus 1 would give you 1 byte over and give you 17. That's if you referred to it as a pointer. But yes, fundamentally that's correct. You would run into trouble if you tried to set it to a value that is too much. So cars, if we refer back to our list of data types, can only be from 128, negative 128 to 127. If you tried to store 256 in there, you'd end up going past the amount of space you can store in 1 byte, the amount of information you can store in 1 byte, and you'd run into a buffer overflow of a different kind. Now, what's a string then? This is another very common data type. And in C, much like arrays, strings are just pointers, but they're pointers made of cars. We were just discussing this. Cars have a size of 1 byte. If I just declare a car first underscore car equals A, then I'm going to say 1 byte's worth of space on my stack, because it's not a pointer, it's not a malloc to mount, so it doesn't go on the stack, or it doesn't go on the heap, it goes on the stack. We're going to say that value is going to be the binary corresponding to A. I could have an array of cars, which will also go on the stack, and I could declare it like so, and say that I've got 6 cars, and they are AGNES, which might happen to be the name of one of my other cats. But then we have something else at the end here. This is called the null terminator. This is the null character. That means the string is over. There's nothing past this point in the string. In C, you need to terminate your strings with this so that functions like this one, stern copy, know how long your string is. That's a more complicated topic, but just know that whenever you have a string in C, you need to give it 1 more character's worth of data than what you actually need, and you have to set that last character to 0. Now, if I wanted a pointer to a string, if I want a string that's going to live on the heap forever, then I would say car star cat underscore name equals casting it to a car again, and then size of car, which as we were pointing out before is 1 byte times 6. So this will give me 6 bytes on the heap, and it will tell me where that first byte out of the 6 is, store it in the variable cat name. Then if we want to store a string in there, we have to call a function, stern copy. Because in C, there's no such thing as strings, there's just cars. So all we have are functions that manipulate cars and treat them like sets of strings if they're pointers. So we copy into the pointer cat name. If you were to look at the requirements for this function, it wants a pointer here. You're going to copy in this string, Agnes, and then it's 6 bytes long. So in that 6th byte, the N here stands for null. It's going to put this null terminator for you. This should stay stern-len, which is a null terminated string, because stern-len is not secure. It doesn't guarantee a null at the end. But essentially, you need to tell C, in C, you need to tell the system and all the functions that you call where your string ends. Again, you need to have that null terminating character. So let's look at what the memory looks like when we do this allocation of a string. It's going to look something like this. Now these numbers, as I'm noticing, are also not correct. This should be 16, 17, 18, 19, and so forth. So we can actually adjust that real quick, just so that you can see the accurate information. It should be 17, 18, 19, because cars have a length of 1, 20, 21, 22. There we go. very important that that's accurate. So again, we've allocated our 6 bytes, our 6 cars. We've copied in this data, AGNES, and then the null terminator, 0. And we know that it's allocated, and we're pretending that it's a car. That's the same as what we did with the integers. It's exactly the same idea. It's just using a different data type so that we can store a different kind of information. When we use string copy or string len to decide the length of our string or to put a string in here, we're just knowing that we start at address 16, which is what this stores, and we go 6 from there and put a null terminator at the end after this data. Anything beyond that that's not allocated, it's garbage. We don't know what it is. We don't care. Now, what if I want to store something that's not a string or anything else that's built into the language in that way? Arrays are built in, ints and cars are built in. Strings are kind of built in, as you see, because there's standard library functions for them. What if I want my own thing? What if I want to store information about my cats? As you've seen, I'm obsessed with my cats. Can't help but talk about them all the time. So I want to store information about them programmatically. I don't have a data type in which I can easily do that and represent all the different kinds of information about them. So I can create what's called a structure. I can declare a structure called a struct in C, much like this. I've got a cat struct. It's got 2 components to it, an integer, which is a weight, and a pointer to a set of cars, which is their name, a string that represents their name. Now, you might look at this and think, wow, that looks a lot like an object. That looks like an object, a class in C or C# or Java, an object that you would define in JavaScript. Looks very similar. The difference is that structs are sets of known data types, including other structs. And they are not allocated like objects automatically. We're going to look at how they're allocated. You could treat them like an object and that they're allocated as a reference, which in C is just a pointer, or they could just be considered like any other variable. Let's look at what this means. Here's some code where I use my new struct. In this case, I'm just declaring this struct as a variable that goes right on my stack, as if it were an integer or a car or anything else. So I can say I've got a cat struct called Big Scout. That's going to tell the system, give me enough memory to store 1 integer and 1 car pointer's worth of data. And then I'm going to start setting what I want at those places. So I set her weight to 12 pounds because she's a big one. And I set her name. I'm going to get myself a pointer to a string that stores her name. So remember, what's going here in name? It's just the pointer, not the actual string. The actual string is going at whatever memory address we allocated. It's the address the pointer refers to. How are we going to set that? Well, we're going to use string copy again, but we're going to refer to bigscout.name. So what is Big Scout? Big Scout is just another variable, another piece of data that lives on our stack. It's exactly the same as an integer, except that it's got more stuff in it, and so it's bigger, and that we've decided what the stuff is. That's all. We've said, okay, we have a thing called an integer that's at the beginning of this structure. So at the start of the structure, at the first byte of it, we're going to set 4 bytes equal to 12. And then we're going to set however many bytes the pointer is worth after those 4 bytes to name. And that's going to be a pointer. And that's all we've decided. It's just a variable like anything else, and we've decided what it means by defining it. What if we want to make this into a pointer? We do it exactly the same way. But now, when we do an allocation like so, we have a reference to a memory address where we can find this much data. Now, what's going on here in size of? What does that mean? Well, when you do size of on a structure like this, we're going to look at the sizes and the ordering of these parameters, these properties that we've put inside the structure. So an integer is 4 bytes. A pointer, again, the size varies, but let's say that a pointer needs 8 bytes. So in that case, the total size of this structure would be 12 bytes. We'll allocate 12 bytes of memory in which to store this data. And what will that data look like? It'll be 4 bytes worth of integer and 8 bytes worth of pointer to a character. That's all. It's going to be allocated exactly the same way as everything else. We're just saying that we know what each little part of it means, and we're going to get it back here as a pointer just as we would a pointer of any other kind. When we want to set values into it, we're going to do that exactly the same way, except that we use this syntax, the arrow operator, which is a hyphen or a dash and then an arrow. The arrow is actually, I guess it's the greater than sign. We're going to use that to say, this thing is a pointer. I want to go to the memory that that pointer references and then go this far in. Tell me the point in that memory where the weight value is defined, and I'm going to set that to 12. Tell me where the name value is defined. I'm going to set that to be this pointer. And then I'm going to copy into that same place the name Scout, plus, of course, my null terminator, so 6 characters worth of string. Now, how can we use this to create other kinds of data structure? We can do that by simply declaring structures that reference themselves. A linked list, as you probably know, is just a bunch of nodes, and each node tells you where the next node is, so that you can go through those nodes and go from the beginning of your list to the end of your list. A linked list in our code can be defined this easily. It's a structure that has a pointer to another structure of the same type, which is the next node in our list, and it's got some data. We'll come back to that data in a second, but we've got some data in there. Okay, so we've got our first node here, first node.next equals, here's that ampersand, that's our address operator. It equals the address of the second node. And the second node.next equals 0. As I mentioned before, 0 is a special address. 0 is simply the null pointer address. There's nothing at memory location 0. Memory location 0 never exists. Likewise, we can allocate those linked list nodes in just the same way we've allocated everything else. And then we can set our pointers to be those same sets of addresses. There should be a star here, but otherwise, you can set your pointers to those same sets of addresses. And all of a sudden, you've got a linked list to arbitrary data that you've allocated that lives on the heap. That list will live in memory forever until you free it. And likewise, we can put car data in here, A, B, and so forth, or we can put string data, car star, which can be allocated in the same way we've allocated everything else. So you can have a structure that has 2 pointers in it, and those pointers refer to different pieces of memory. This is how you can have these disjointed pieces of memory, but you're storing the list of addresses in the same place. You can go through every piece of memory, every node of this list by just going next and next and next. And you can look at the data in each of those. So I mentioned before that you need to clean up your memory. Well, how do we do that? Scout has, in her beneficence, given us another great function called free, that you pass it in any kind of pointer, and it will unmark, take this allocated bit here, and turn that off. It's no longer allocated. We don't change the data. The data is just the same data as it was, but we can now say, okay, I can use this to store something else if I want. If you don't free, you're just going to keep using memory forever and ever until your system runs out of it. That's called a memory leak. If you've ever looked and seen Chrome using 8 GB of memory to store one tab, there was probably a memory leak. You probably didn't free up, Chrome didn't free up all of the memory that it was supposed to have. So you must call free whenever you use a malloc. Every malloc has to, somewhere else in your code, have a corresponding free, or you're going to be in trouble because you're not going to be freeing up all the memory that you've allocated. Your program will keep accumulating memory forever if you run it enough. This is one of the most common pitfalls that people fall into when they're writing code in C. Because remember, that memory on the heap lives forever until you tell it otherwise. So that'll look something like this. If we malloc our int, our array of 4, we need to call free array of 4. We don't need to tell it the size again. We know how much size it is because Scout is remembering. Likewise, you allocate that linked list, the string within there, you need to free that string. But this, because it's not a pointer, this goes on the stack. It's not allocated. There's no malloc here. So we don't need to free this. We only need to free stuff that lives on the heap, such as this car. But if we did malloc our structure and also our string inside the structure, we need to free them both. And we've got to free them in this order, the name before the structure the name is contained in, because if we don't, then we're going to run into trouble. Once you free this, the data is now garbage. We don't know what it is anymore, and you won't be able to find this to free it. So you also have to free in order. You have to free your data in the same order that you allocated the data. I don't know why this is, there we go. What else can you do with all this sort of thing? What else can you do with all these pointers? Well, there's a ton of other stuff you can do. Again, as I mentioned, and we didn't have time, unfortunately, to go into it, but pretty much any data structure, hash maps, graphs, trees, all of these things can be implemented just with pointers. If you can build a linked list in an array, you can build any of those things. And there's ways to do it in C, all of which is just purely based on pointers. You can also do things like out parameters. I'm not going to go into how this works exactly, although if you ask and we have time, maybe I can discuss it a little bit. But if you have a pointer to another pointer, you can use that as an out parameter. You can set that to a value, return that out of your function, and it will work the same way as the out parameter in C# works, for example, where you can say out whatever my variable, and it will set that in the function in your method and send it back to you. That's also called multiple indirection. You can have pointers to pointers to pointers. You can have pointers to functions. So a function, such as any of the ones that we've declared, that get cat count function, the entry point to that, the place where you go to get into that function, is itself a pointer, and you can define interfaces. They're not really interfaces, but they act like them, where you just have a set of function pointers that you change to go to different functions depending on the context. And there are some special advanced data structures in C that you can use in this way as well. There's a data structure called a union that lets you interpret pieces of memory as being different things, more or less at the same time or contextually based on whatever you want, in an even more free and less way that doesn't involve any casting. And there are iterators where you can go, if you want to do a for each, for example, well, C's equivalent of that would be to use an iteration pointer in a while loop. All of these things, I know I'm going through them really fast. These are all things we can go into more detail in another talk, but again, you can do all kinds of stuff with pointers. All these things that underpin how languages work and how programming works are all made possible through pointers. Direct manipulation of hardware in your system, often hardware registers will be represented as pointers. The address where a sensor, for instance, is storing some data will be represented as a piece of memory that you can have a pointer to, and you can refer to that data. And as was asked before, you can simply access memory directly. You can use it as unstructured memory that has whatever you want in it. You don't have to even give it a type. You can say, put this amount of binary in this piece of memory, and that'll work. That's all you have to do, really, because that's all it's doing under the hood. It's just helping you by telling you the types and enforcing them. So you can do all kinds of things with pointers that lets you fundamentally create essentially any kind of data type that you want, any kind of structure that you want, any kind of programming concept that you want. And this is what all the languages that you use every day are doing under the hood at some level, even if they're very far up on the chain of abstraction. And so it's the operating system doing it for you. Where can I learn some more about this? There's a whole bunch of resources. I think the slides will be made available after this talk, so I won't go through them one by one. I'll just mention that Learn C the Hard Way by Zed Shaw is a good place to go if you want to learn to write C safely. I don't know that I can recommend Zed Shaw as a person. He's kind of abrasive, and the style of the book is kind of abrasive, but I can represent to you that the content is really good, and it will help you really understand it. This Yale class, 223, Computer Science 223, is really great as well, and will teach you all those different data structures that I touched on just a little bit in much, much more detail. And there are some great code bases you can look at. A whole bunch of examples in this thread, or this GitHub repo for a game engine called Permafrost is great. You can read the code and see how they use pointers. The last thing I'll mention is that, of course, there are other languages you can use to do this, C++ and Rust. And those both use pointers in ways that are similar to, but distinct from C. C++ has objects in it that are real objects like Java. Rust requires safety. Buffer overflows and memory leaks will be very unlikely to occur in Rust, because Rust won't let you do that. Rust is much more careful about allowing you to allocate memory or not. Whew. So with all that said, I know that was a lot of information in a relatively short amount of time. I appreciate you all sticking with me through this, and I would be totally happy to answer any questions if there are any. I know we're a little over time. I'm willing to stick around if you want. If not, I don't judge you. I know that was a lot of information. The slides will be made available later. You can also always email me after the fact if there's things you want more references or resources for, or if you have questions as a follow-up on this. happy to chat with you. My email's right there. And I'll just mention that my current employer, Olo, is hiring. You will not have to do a lot with pointers if you work at Olo, but I can tell you that the problems we have are big enough and complicated enough that you'll be glad you have that underlying knowledge, even though you may not be doing it in your day-to-day. I really appreciate everybody sticking with me through this talk. I hope you learned something useful. I hope you'll be able to take it and bring that forward into the rest of your studies. Wish you the best of luck with all of that, and I really hope that it's helpful to you. I hope you have enjoyed Scout's presence as well. As you can see, she's very happy to have met all of you. And by very happy, I mean she slept through most of this, but that's most of what she does. If there are any questions, totally happy to answer them through the Q&A now, and I'll stick around for a minute. Otherwise, thank you so much, and I really appreciate you coming.
Thank you so much, Max. We all really appreciate the talk, and thank you for spending all this time with us. It's a very in-depth and very interesting talk. I never really knew pointers had this much depth and complexity to them, and it was a part of C++ and C that I've never explored before. So it was very good to know, and I'm sure that the audience thinks so too.
Well, thank you guys for coming. I really appreciate it.
If anyone else has any questions, we can answer those, but if not, that will.
I'm not seeing any right now.
Yeah.
Well, you can always email me later in any case.
Yeah. The slides will be in additional resources link that will be in the event description. So just so you guys know. And yeah, thank you again, Max, on behalf of everyone at Labs. We really appreciate all the work you put into both of these talks. Thank you.
Thank you. All right. Bye, everybody.
Have a great day, everyone.